in the last lecture we had introduced the profile analysis for this multivariate data, and we had posed the following questions 1, 2 and 3, and we had discussed in detail how we actually go through answering these questions sequentially. And we had also put these questions that are of interest in profile analysis in terms of statistical hypothesis testing. So these questions were translated in statistical terms, and we had this H01 the first hypothesis, H02 the second hypothesis, H03 the third hypothesis that is to be tested in order to answer the questions associated with the profile analysis. And we had also said what is the sequencing actually when we are talking about this three sets of hypotheses H01, H02 and H03. H02 is to be tested only if we have H01 accepted. H03 is to be tested only if both H01 and H02 in that order are accepted, and hence we go to the third hypothesis testing. Now what we will see today is we will look at how to perform these tests H01, H02 and H03 using the Hoteling's t-square statistic. We will also see some numerical examples of some actual profiles, and then perform the profile analysis questions that we have in mind in order to see how these questions are answered for some practical data sets. So let us move forward to looking at testing of H01 first, but before that we will have to have the following assumptions. So we make the following assumptions for testing. The underlying assumptions is that this group 1, which is the first population, so this is the first population, let us have that being characterized by a multivariate normal m dimensional. Say I will write that as normal multivariate normal m. We had denoted that by perhaps eta yesterday. So this eta vector and a covariance matrix sigma, where the sigma is positive definite, and the group 2, the second population, is also a multivariate normal distribution with mean vector as nu vector and sigma as its variance covariance matrix. So we keep this sigma in both the populations to be same. So we have two populations, group 1, group 2, which differ in their mean vector component, the variance covariance component remaining the same. So we have n1 observations from group 1. The random variables, let them be denoted by x11, xn1, 1, and n2 observations are taken from group 2. So we will have this random sample coming from the second group here. So these are denoted by x1, 2, xn2, 2. So these two are the two random samples. So this is the random sample set, and this is also the random sample set from the two respective populations. Now these are forming an independent set of random vectors, and so will be these forming set of independent random vectors, and these two also are the two random samples from two groups, and hence they are also going to be independent. Now the sample statistic, that's what we have derived from these two, is x1 bar. Let me denote that by x1 bar in order to signify that it is basically coming from the first population. So this is 1 upon n1 summation I equal to 1 to up to n1, and then we will have this xi1. Similarly, what we will be having is x2 bar vector, which is the sample mean vector coming from the second population, and we will have n1 minus 1 S1. This is S1 is the sample variance covariance matrix when it is based on the random sample coming from the first population. So this is equal to summation I equal to 1 to up to n1 x I1 minus x bar 1 vector, this multiplied by x I 1 vector, this minus x bar 1 vector, its transpose. Similarly, we will have n2 minus 1 times S2, which is the sum of squares and cross product matrix similarly from the second population. Now, from the distribution theory, what we know are the following quantities, that this x1 bar, this follows a multivariate normal m dimension with a mean vector as eta vector, the underlying mean vector of that population, and this sigma divided by n1. From the first sample itself, we will be also be having n1 minus 1 S1, this to follow a Wishart m n1 minus 1 sigma. The two are independent because they are based on that random sample x from the first population. Similarly, from the second population, we will have these characteristics, the statistic x2 bar. This would follow a multivariate normal with nu vector as its mean vector and a sigma upon n2 as its variance covariance matrix, and we will also be having n2 minus 1 S2. This would follow a Wishart distribution m n2 minus 1 and the variance covariance matrix same as the previous Wishart matrix. These two also are going to be independent, and furthermore, because we have this, the first set of statistic coming from the first, based on the first set of random samples from the first population, and the second set here coming from the second population, we will have further independence of these statistic as well, right. Now, once we have this, we can say that this would imply further that x1 bar minus x2 bar, this would follow, this is a random vector of the same dimension as that of the underlying multivariate normal distribution, this, that is m. So, this will have a multivariate normal distribution m dimension on mean vector as eta minus nu vector and a covariance matrix sigma by n1, this plus sigma by n2. So, this reminds us of the two sample normal problem basically. So, that this is multivariate normal eta minus nu vector and this is sigma is common. So, we will have this as n1 plus n2, this divided by n1 times n2. Let me keep it up to this particular point, we will require that further also. Now, we will look at the pooled sample variance covariance matrix. Why do we look at the pooled sample covariance matrix? Because we have sigma, the underlying variance covariance matrix of the two populations, to be exactly the same, and hence we can look at the pooling of the two data in order to obtain an estimate of the sample variance covariance matrix. So, pooled sample variance covariance matrix, variance covariance matrix is what we have, that is n1 plus n2 minus 2 times S, say S is the pooled sample variance covariance matrix, and that would be given by n1 minus 1 S1, this plus n2 minus 1 S2. So, that would be given by the two separate sum of squares and cross product matrices. So, the first one would be this and the second one similarly would follow. So, that this is equal to, let me make it complete, I equal to 1 to up to n1 x I1, this minus x bar 1, this multiplied by x I1, this minus x bar 1 transpose, this plus the sum of squares and cross product matrix coming from the second population, this is x I2 minus x bar 2, this multiplied by this x I2 vectors minus x bar 2 vector, its transpose. So, this is what we have as the pooled sample variance covariance matrix. It is easy to see that since this has got a Wishart distribution, Wishart m n1 minus 1 sigma, and this part has got a Wishart distribution m n2 minus 1 sigma. So, we will have, and the two Wishart distributions are independent. So, we will have the distribution of this sum of two independent Wishart distributions with the same variance covariance matrix, to be given by also a Wishart distribution. So, from the properties of Wishart distribution, we will have the following, that n1 plus n2 minus 2 times s. This would follow by the additive property of the Wishart distribution, that it is Wishart m n1 plus n2 minus 2 and with the same variance covariance matrix sigma. So, the two things that we are going to use in all the testing procedure is, this is one here, that we will have x1 bar minus x2 bar to have this multivariate normal distribution, and we will have this to follow a Wishart distribution, right. Now, in the light of this discussion, let us now move forward to testing of H01 first, because that is the first hypothesis that one needs to test, testing of this H01 hypothesis. Now, what is H01 hypothesis? H01 hypothesis, if we remember, it is eta k minus nu k, that is equal to eta k minus 1 minus nu k minus 1. So, this is going to test the parallelity of the two profiles in the population. So, this is k is from 2 1 to up to p, right. Now, this is equivalently written as, through a matrix H01 which is A times eta vector minus this nu vector, that equal to a null vector. Now, what is this A? Where this A matrix is of the following structure, that it will have 1 minus 1 zeros, then the second row is 1 minus 1 0, and finally the last row is what is going to be given by this minus 1 1. So, if we have this order as m by 1, this is going to be an m minus 1 cross m matrix. This is a matrix of constants. So, if we have A defined as 1 minus 1 1 minus 1 like this along this block here, so what we are going to get here is that from this first element, remember that this eta and nu are the corresponding mean vectors of the multivariate normal distribution, and hence the first element would be eta 1 minus nu 1, and the second element would be eta 2 minus nu 2. So, the first row here, when multiplied with that vector, would lead us to having the first element, that is eta 2 minus nu 2 is equal to eta 1 minus nu 1. So, we will have all these to be equal, and thus this basically is giving us the hypothesis of interest to be tested. This is to be tested against the alternate hypothesis HA1 say. This is to be tested against HA1, which is A eta minus nu, this is not equal to 0. So, this is the hypothesis to be tested. Now, from the distribution theory, we had this distribution that x1 bar minus x2 bar has this distribution. We will make this transformation that A times x1 bar minus x2 bar. What is the distribution of this? Now, this A matrix is m minus 1 cross m. So, this is a matrix of constants. So, we will have this to have a multivariate normal on m minus 1 dimensions, and the mean vector would just be A times eta minus nu. And what happens to the variance covariance matrix? We had the previous variance covariance matrix as this particular term. So, we will have A sigma A prime, and hence this would be n1 plus n2, this divided by n1 n2, this is A sigma A prime, where the matrix A is known to us. Now, it is important to note that this would have a multivariate normal m minus 1 with a mean vector equal to a null vector, and a covariance matrix as n1 plus n2 by n1 plus n2 A sigma A prime. This is the distribution of this quantity on the left hand side under the null hypothesis H01. Why? Because this mean vector of this random vector here is what is specified as a null vector under the null hypothesis. So, we will have that is all right, and then we will also look at similar transformation to this particular Wishart distribution. This will also imply the following, that we will have n1 plus n2 minus 2 A S A prime, because S had n1 plus n2 minus 2s had a Wishart distribution. So, if we pre and post multiply, pre-multiply by A the matrix of constants and post multiply by A transpose, the transpose of that same matrix of constants, what we are going to have is also a Wishart distribution with the dimension as m minus 1, degrees of freedom remaining the same, n1 plus n2 minus 2, and the associated variance covariance matrix now becomes A sigma A prime, right. So, we will use the two, this distribution under the null hypothesis and this distribution under the alternate not under the alternate hypothesis, this is corresponding to the Wishart. So, let me just copy it once again here, so that we have all the things before us. So, this x1 bar minus x2 bar, this to follow a multivariate normal m minus 1 with a null vector as its mean vector, and the variance covariance matrix as n1 plus n2 by n1 n2, that into A sigma A prime as its variance covariance matrix, this under the null hypothesis H naught, and this is always the distribution of this. Now, we can frame the Hoteling's t-square. Remember, we had defined Hoteling's t-square with two sets of random variables, one which was having a multivariate normal distribution and the other which was having a Wishart distribution. So, we have exactly the same setup out here. So, we will have Hoteling's t-square statistic to be given by this t-square, which is going to be C. Now, C inverse is this particular term. So, we will have n1 n2 by n1 plus n2, this serving the purpose of the C which we had defined for the Hoteling's t-square, this into n was the degrees of freedom. So, the degrees of freedom here is n1 plus n2 minus 2, and then we have the transpose of this. So, the transpose of this is A x1 bar minus x2 bar, transpose of that. Now, that multiplied by the inverse of the Wishart here, so that this is that n1 plus n2 minus 2, this entire term now is having that Wishart distribution. So, we will have inverse of that, and that multiplied by this A x1 bar minus x2 bar, this term. So, this is the Hoteling's t-square on what degrees of freedom? The degrees of freedom is the associated degrees of freedom of the Wishart distribution. So, this is a Hoteling's t-square on n1 plus n2 minus 2 degrees of freedom. It is easy to see that this term cancels out with this one, and what remains is what we have as the Wishart distribution. Note that we cannot do anything further on the inverse of this A transpose matrix, because A is a rectangular matrix. So, we will have this on n1 plus n2 minus n1 plus n2 minus 2 degrees of freedom. And then what we will be doing further is that this would imply that this t square divided by t square by n. Now, n is the degrees of freedom, that is n1 plus n2 minus 2, that multiplied by n minus m plus 1. So, n is the degrees of freedom, that is n1 plus n2 minus 2, this minus m. Now, m is what? M was the dimension here is m minus 1, this plus 1, that divided by the dimension which is m minus 1. So, this is t square by n minus m plus 1 by m. Now, this will follow a central F distribution under the null hypothesis with the degrees of freedom as m minus 1, and whatever this comes. So, this is going to be n1 plus n2. So, this 2 cancels out with this plus 1 here and another plus 1 out here. So, we will have n1 plus n2 minus m, this under the null hypothesis H naught, right. So, since we have the null distribution of t square multiplied by this particular constant to follow a central F distribution on m minus 1, n1 plus n2 minus m degrees of freedom, the testing of under H naught 1 actually, here also H naught 1, the hypothesis to be tested here is H naught 1, and hence we will reject the null hypothesis. This implies we will reject H01 if observed value of this t square that multiplied by this term is n1 plus n2 minus m, that divided by m minus 1 into n1 plus n2 minus 2, if the observed value of this quantity is greater than f m minus 1 n1 plus n2 minus m alpha, where this particular point here is a given point which is the upper alpha percent cutoff point of a central f distribution on m minus 1 n1 plus n2 minus m degrees of freedom. So, that is how we are going to test this H01. We will reject H0 at, of course, level alpha and with the associated level at alpha if the observed value of this is greater than this, and accept otherwise. So, we have been able to obtain the testing for the H01 hypothesis, the hypothesis which tests similarity or parallelity of the profiles from this particular Hoteling's t square statistic. So, that is it for the first set of testing problem. Now, the second hypothesis of interest was to test H02. Now, remember that we will only test H02 if the first hypothesis is accepted. Suppose H01 is accepted, then we test H02. If H01 is rejected, then we do not test H02, we stop at that particular point. Now, this H02 as it was given earlier was equality of the profiles, and that is what we have out here, that this is the hypothesis of interest for k equal to 1 to up to p. Now, this is equivalent to, once we have H01 to be accepted, when H01 is accepted, then this H02 is equivalent to the hypothesis H0 prime, which is summation eta k equal to summation of these new k values, k equal to 1 to up to p, k equal to 1 to up to p. Now, this is to be tested against the alternate hypothesis HA2 prime, which is summation eta k is not equal to this summation nu k, under the condition that H01 already is accepted. So, this thus is going to test whether the two profiles of the groups are actually equal, given that they are similar or they are parallel, right. Now, this hypothesis is H02 prime, this is 1 prime eta vector equal to 1 prime nu vector. This is to be tested against HA2 prime, which is 1 prime eta vector not equal to 1 prime nu vector. This, or in other words, what you can write is that this is 1 prime eta minus nu vector, that is equal to a null vector. So, this is H02 prime, which is this. This is to be tested against HA2 prime, which is 1 prime eta minus nu vector. This is not equal to 0. So, the testing for this second hypothesis H02, that is what is testing the equality of the profiles given that the two profiles are similar or parallel, reduces to this particular problem. Now, the point in reducing this particular H02 in this form is to tally this particular problem of testing this hypothesis with the previous problem that we had tackled and discussed in detail, that we had the H01 hypothesis given in terms of this sum matrix A of constants times eta minus nu, that to be equal to a null vector, to be tested against that this is not equal to a null vector. Now, as we see, the H02 hypothesis, we have cleverly reduced it into a form which is exactly same form as that of the previous one, with the previous A being replaced now by 1 prime. So, the testing follows exactly in the same way. So, we take A equal to 1 transpose in the previous formulation, in the previous derivation of the test statistic to get Hoteling's t square and the associated test, right, and hence we can straight away use this particular test statistic what we had got there with just A being replaced by 1 transpose. So, the Hoteling's t square statistic would exactly look like the same with A being replaced by 1 transpose. So, this would imply that first up the Hoteling's t square statistic is now this t square, which is now going to be given by n1 n2, that divided by n1 plus n2, which was previously there, and what we will be having here is 1 transpose x 1 bar minus x 2 bar whole transpose, and then we had that A S A transpose. So, we will have 1 transpose S 1, this is that vector out there. So, you can, if you want, you can just put this vector sign here. So, we will have this, and then inverse of that multiplied by the transpose of this vector, this actually is a scalar quantity, 1 transpose x bar 1 minus x 2 bar, right. So, that is the Hoteling's t square statistic in this testing problem H naught 2 prime, and then we can say that what is the test statistic. Now, here what we will be having is t square divided by n1 plus n2 minus 2, that what we had was n1 plus n2 minus this term. If we look back here, this we had as n1 plus n2 minus m. So, we will have the same term here. Now, what is m here? M is going to be equal to that term there. So, that this is n1 plus n2 minus 2, this minus m minus 1, m minus 1 is nothing but 1 here, this plus 1, this divided by 1, because that is m minus 1 is equal to 1 here. This would follow a central F distribution on 1 n1 plus n2 minus 2 degrees of freedom under the null hypothesis H naught 2 prime, and we will reject H naught 2 prime at level alpha if observed value of this t square. So, this cancels out. So, what we will be having is just this n1 plus n2 minus 2 also will cancel out. So, if the observed value of t square only is greater than f1 n1 plus n2 minus 2 alpha, where this point is the upper alpha percent cutoff point of a central F distribution on n1 plus n2 minus 2 degrees of freedom, and accepted if otherwise. Accept H naught 2 if otherwise. So, using the similar type of derivation as to what we had used for the first H naught 1 hypothesis, we have obtained the test statistic and the testing procedure for testing the second set of hypothesis, testing for the equality of the two profiles. Then we move on to the third set of hypothesis of interest. What we had there was testing for H naught 3. Now, testing for H naught 3 was eta 1 equal to eta 2 equal to eta, what was the dimension, m, that equal to nu 1 equal to nu 2 equal to nu m, against that they are not equal. So, this is to be tested against H A 3 that they are not equal, all of them are not equal, right. Now, remember that H naught 3 is to be tested only if both H01 and H02 in that order, H01 and H02 are accepted. So, if after H01 being accepted, we have moved on to H02 and then we have observed that H02 is rejected, then we will not proceed for testing of H03 and we will stop at that particular point. If H02 also is accepted, then we will move on to testing this H03 hypothesis, which is going to test whether the common profile, that is what we have, is a level profile, that is all of the components are same. Now, let us see how we can we are going to test this particular hypothesis. Now, this H03 we can write it as following. Now, let me first give this notation. Suppose, now since we are only testing H03 when H01 and H02 are accepted, equality of the two profiles would imply that there is a common profile. Suppose this mu vector, which is denoted by mu1, mu2, mu m, denote the common profile of the two groups. So, if we have this to denote the common profile, then H03 is what we are trying to test as a mu equal to a null vector. This is to be tested against HA3 that a mu is not equal to a null vector. So, we are testing this at a mu is not equal to a null vector, where a is as what we had used previously. So, this can be, now remember that there is no uniqueness in defining this particular matrix of constants A. A can alternatively be defined in order to translate the hypothesis that all the components are equal also. So, that there is no uniqueness in representing this particular A matrix. This is a -1, 1 previously and all zeros before that. So, this is an m minus 1 cross m matrix of constants. So, this is now the hypothesis of interest. What we are going to test is that the common profile what we have, which is being denoted common profile between the two groups. Now, that is we are going to test that all the components are equal, and through this matrix A we are having mu1 equal to mu2, mu2 equal to mu3, mu3 equal to mu4, m minus 1 equal to mu m, and thus we have all the components to be equal. Now, let z bar denote the pooled mean, random vector, where this z bar is given by. So, since it is a pooled mean, we will have that to be equal to n1 times x1 bar plus n2 times x2 bar. So, this is going to give us the sum of all the observations, that divided by n1 plus n2, right. Now, when we have this being defined, note that this is just n1 by n1 plus n2 times x1 bar, which is having a multivariate normal distribution, that plus n2 by n1 plus n2 times x2 bar, which is also having a multivariate normal distribution. The two are independent. So, this would imply that this z bar, the pooled sample mean random vector, will have a multivariate normal distribution with mean vector as n1 times the mean vector of this, which is eta, this plus n2 times this new vector divided by n1 plus n2. So, that is what is the mean vector corresponding to this, and then the covariance matrix of this element would be n1 by n1 plus n2 whole square. This is a scalar constant, that multiplied by the variance covariance matrix of x1 bar, which is sigma divided by n1, this plus n2 by n1 plus n2 whole square, that multiplied by the variance covariance matrix of x2 bar, which is sigma by n2, right. Now, we have this particular term, some simplification can be done, that is, this is a multivariate normal distribution, n1 eta, this n2 new vector, this divided by n1 plus n2, So what we see here is that one n1 gets cancelled out with this one and one n2 gets cancelled out with this one. So if we take sigma outside, we will have an n1 plus n2 in the numerator and n1 plus n2 whole square in the denominator. So what this will lead us to is that this is 1 upon n1 plus n2, one of them cancels out, that multiplied by sigma. Now since we have the two hypotheses sequentially being accepted, H01 and H02 being accepted, we have these two eta vector which is leading us to the profile of the first group, and this eta and nu, both of them are accepted to be having a common profile, and hence we can replace them by mu, and hence what we will be having is the following: since H01 and H02 are accepted, we have a common profile. We have a common profile mu, which would imply that our z vector, the pooled mean vector, has got a multivariate normal distribution with a mean vector what? If we look back here, if both of them are replaced by mu, then the mean vector of this pooled sample mean would just be equal to mu, and the variance covariance matrix to be equal to 1 upon n1 plus n2 times sigma. And what we also have is this quantity, which is, we have already seen it, that n1 plus n2 minus 2, the pooled sample variance covariance matrix. This has a Wishart distribution, Wishart m n minus, it's n1 plus n2 minus 2 as its degrees of freedom and sigma as its associated variance covariance matrix. So we have the two distributions, z bar being a multivariate normal and n1 plus n2 minus 2 times s, where s is the pooled variance covariance matrix, to have a Wishart distribution this. Now since we have this s to be independent of x1 bar and x2 bar, this z bar, which is the derived random vector from x1 bar and x2 bar, that is going to be independent of the pooled sample variance covariance matrix, and hence these two distributions, we can say that these two are independently distributed. Now let us go back to what we have to test. The null hypothesis we have translated as a mu equal to a null vector against a mu is not equal to a null vector. So we need to introduce this a somewhere here. So from these two, what we will be having is that a times z bar vector. Now a is a matrix of constants, which is m minus 1 cross m dimension. So this random vector is going to be a random vector of dimension m minus 1. It is going to have a multivariate normal distribution with a mean vector as a mu and a covariance matrix as 1 upon n1 plus n2 times a sigma a prime, and we have a similar, we make a similar transformation to this Wishart matrix here. So we will have also n1 plus n2, will also have n1 plus n2 minus 2, that into a s a transpose. This will have a Wishart distribution on the dimension m minus 1 with the degrees of freedom as the previous degrees of freedom of that n1 plus n2 minus s Wishart matrix, and with the variance covariance matrix now being given by a sigma a prime. And since the previous two distributions were mutually independent, we will also be having the distribution of a z bar and this quantity here to be independent. So we have once again the constituent parts actually to frame the Hoteling's t-square statistic, because in the Hoteling's t-square statistic we have one a Wishart distribution and the other having a multivariate normal distribution. The independence of the two will actually lead us to forming the Hoteling's t-square statistic. So using these two, the Hoteling's t-square statistic would turn out to be the following: Hoteling's t-square statistic is going to be given by t square, which is going to be equal to c times n. Now c is what? C is the inverse of this particular quantity. So we will have c as n1 plus n2. Then comes the degrees of freedom associated with the Wishart. So that this is n1 plus n2 minus 2, and then we will have the transpose of this. So we have a z bar transpose, and then the inverse of the Wishart matrix, which is for the given case n1 plus n2 minus 2 times A S A transpose and whole inverse of that multiplied by this vector which has got the multivariate normal distribution. This is A Z bar. So, what is that we get? We can see that this cancels out, and this is just equal to n1 plus n2 times A Z bar transpose A S A transpose whole inverse. A is that rectangular matrix which we have in H naught 3. So, this is multiplied by A Z bar. So, this is the Hoteling's T square on what degrees of freedom? Degrees of freedom is the same as that associated with the associated Wishart distribution on this degrees of freedom. So, if we have that, we can also say that furthermore this T square divided by its degrees of freedom n1 plus n2 minus 2 multiplied by degrees of freedom n1 plus n2 minus 2, then minus m here is m minus 1. So, that is m minus 1 plus 1, this divided by m minus 1. So, this is going to follow an F distribution central under the null hypothesis H naught 3 only. So, we will have that to have an F distribution m minus 1 as the first degrees of freedom. Let us see what is the second degrees of freedom. This is plus 1 minus 2. So, that cancels out, and what we will be having here is n1 plus n2 minus m under the null hypothesis H naught 3. Now, under the alternate hypothesis actually this statistic will still have an F distribution, but it will be a non-central F distribution. So, since we have the distribution of this statistic, the null distribution, to have an F distribution, we have the testing procedure that we will reject H naught. So, this term here 1, minus 1 and minus 2, these terms cancel out, reject H naught 3 at level alpha if observed value of T square, this multiplied by n1 plus n2 minus m, that divided by m minus 1 into n1 plus n2 minus 2. This is if the observed value of this quantity for the given sample exceeds the upper alpha percent cutoff point of a central F distribution on m minus 1 and n1 plus n2 minus m degrees of freedom. So, this denoting the upper alpha percent point of a central F distribution on m minus 1 n1 plus n2 minus m degrees of freedom, and accept H naught 3 if it is otherwise, right. So, this is how the three testing procedures H naught 1, H naught 2, H naught 3 are going to be tested for the profile analysis questions, the questions of interest to be tested, and they are to be tested in a sequential manner. First H naught 1 if accepted, H naught 2 if accepted, H naught 3 if at any point H naught 1 or H naught 2 are any one of them is rejected, then we do not proceed for testing the next level of hypothesis. And if at the end of H naught 3 all the previous H naught 1, H naught 2, H naught 3 all are accepted, then we will say that we have the profile of the groups to be not only similar or parallel, not only equal, they are also level profiles. Now, what we are going to see next is some actual data analysis based on some real life data where profile analysis is going to be carried out. So, this is what we have here. This is some given data. So, this we have some practical data where the scores corresponding to a psychological test given to two groups of male and female subjects. So, there we have two groups here. The first group is a male group and the second group is a female group, and then the same set of psychological tests, 4 tests actually, are given to both the groups. And then we are interested in type of questions that we have just now answered theoretically in profile analysis. Now, for the male group we have taken n1 observations, which we have n1 equal to 30. So, from the male group we have 30 observations leading us to this sample mean vector which is a 4-dimensional vector which has these as the corresponding constituents. Similarly, for the female group we have got 30 observations with a mean vector computed from n2 observations. This actually should be n2, not n1. So this is from the second group. We should write it as n2. Well, they are same, so it does not matter much, but technically one should write this as n2. This is the mean vector corresponding to the second group. And we, in the profile analysis, we have been assuming all along that the variance covariance matrix associated with the different groups are same, and hence if we do not have that, then the testing procedure for the Hoteling's t-square actually gets spoiled, because at the point of looking at the common sigma, when pooling the two different Wishart distributions, we will have problem there, and the additive property of the Wishart cannot be used in such a situation. So in order to actually have the testing carried out through the Hoteling's t-square, we would require the common sigma assumption to be inserted there. And for the given data here, n1, n2 as 30, 30. So from the 60 observations we have obtained this pooled sample variance covariance matrix from the data. Now we are interested in profile analysis of the two groups. How do we proceed? Now first we would like to see how the profiles of the groups actually are behaving. So we would require the sample mean vectors in order to lead us to those profiles. So this is implemented using a SAS routine. So we are looking at this, basically are the mean vectors inserted in SAS, and then what we have is the following. So we are looking at construction of the profile. These are the SAS statements in order to get to that profile of the two groups. So the profiles, this is going to be the sample profile. Sample profile is what is obtained when we join the points which are associated with the sample mean vectors of the two groups. So this is the profile for the first group in red color here, and the green color denoting the profile of the second group. So this point is basically corresponding to the first group. We will have that to be the mean of the first component in the second group there. So if we look back at the data, it would be clear what these points actually are. So we have for the male group the first mean to be 6.8. So in the profile, sample profile of the first group, we will join this point with the next point here to get the profile of the first group, first direction. So all these points are joined consecutively to get to the first sample profile, and similarly this is going to be, so we see that this is higher than this particular term here. These two are almost the same, these two are almost the same. There is a minor difference between these two, so that we have got this as the sample profile. So we have this a bit higher than this, the second one almost the same, the third one almost the same. There is a minor deviation between the last point of the two groups, right. So this is the male profile, this is the female profile. Now we are going to test the three types of hypothesis that we say that we are interested in. So we have to test the profile analysis hypothesis one after the other. So that we have this as a sample variance covariance matrix. Now this is, we perform this profile analysis using IML procedure of the SAS, and then we will be implementing what theory we have learnt. So this is what is the procedure IML doing. So we are reading all the variable ones into, this is the creating the mean vector for the first group, creating the mean vector for the second group. So first population mean, second population mean, etc. So we will also be requiring to we will also require to have the pooled sample variance covariance matrix, because that's what is going to be used. Then we need to construct that A matrix, what we had set when we had said that we are going to test this H01 using an A matrix 1 minus 1, remember. So this C matrix here is basically having that 1 minus 1 type of structure along the main diagonal block, so that we will have that H01 to be tested. And then once all these are in place, we are testing for the parallel profiles. When we are testing for this parallel profiles here, we have this n1 equal to this, n2 equal to this p, the dimension is 4, and then we will have to compute the Hoteling's t-square statistic. We are looking at construction of computing that Hoteling's t-square statistic, and then we will be looking at the tabulated value of the F distribution. We will compare that with the value which is the tabulated value of the F distribution, and comparing that we will have the Hoteling's t-square statistic being either accepted or rejected. So we have For the parallelity of the profiles, we will require this observed test statistic value for H01. Now, the testing procedure as what is given in this particular piece of program in SAS IML, it is basically going to have that sequential mode of testing, that first we will test H01. If this is accepted, we will proceed to test for H02. If it is not, then we will exit from that particular program at that particular point of time. So, these are the program statements. What is more important is to look at the output of this particular program. Now, remember when we had that profile being given, it appears as if that the two are almost the same. They are of course parallel with minor deviations. So, the point of interest is to see whether that minor deviation actually is significant or not, that will make the two profiles deviating from parallelity and equality of the two profiles also. Now, when we look at the result for testing of the parallel profile, the Hoteling's t-square statistic turns out to be 1.947, and the observed t statistic, which is a constant multiplier of this Hoteling's t-square statistic, turns out to be it is 0.626, and hence the test statistic value is lower than the tabulated value of the F distribution at the respective degrees of freedom, and hence we accept this H01, that is the profiles are parallel. Whatever deviation we have, it is minor deviation basically. Now, once we have this H01 being accepted, then we proceed for testing of H02 hypothesis. So, testing for the coincident profiles only if H01 is accepted, that is what we have. Then we once again have a similar type of programming in order to compute the Hoteling's t-square statistic, and hence to look at the observed value of the test statistic for H02 hypothesis, which is given by this. The output tells us that when we are testing for coincident profiles, this is the Hoteling's t-square, this is the value of the test statistic what we have, and once again H02 is accepted, that the profiles are coincident. Now, if H02 is accepted as what is done here, we will have to proceed to H03, which would test whether the two profiles are actually level, the common profile is level, that is testing for level profiles. Level profiles will test that all the components are same, they do not differ significantly in terms of statistical hypothesis testing. So, one can similarly implement this particular problem here. As what we have seen, sample profiles does not actually lead us to believing that we have got the third type of hypothesis. It cannot be actually accepted that the profiles are level. So, we will have this as the coincident profiles. The result corresponding to this is the second result actually, testing for the level profiles. That level profile hypothesis actually is rejected. We can H03 is rejected at 5% level of significance. We have another example, this is relating to two groups of observations, which is one is a test group and the other one is a control group. We have once again 4-dimensional data here, N1 is 28, N2 is 58, and this the second mean vector, this is x2 bar, is this. We have the pooled sample covariance matrix as this. Now, once again we are interested in profile analysis of the two groups. We see that the sample profile here is of this particular nature, this one corresponding to the control group and one corresponding to the test group. If we once again have to perform profile analysis, we will have to go sequentially in order to test this hypothesis. The SAS output is what is just given here. So, for the testing of parallelity of the profiles of this test and the control groups, we have H01 to be accepted, that is the two profiles are parallel. Then once that is accepted, we will have to test for the hypothesis that they are coincident profiles, that is they have a common profile. So, this basically is the output corresponding to that. Now, as we had seen from the sample profile of the two groups, that they do not appear to a naked eye actually to be a coincident profile. We have the test statistic value, the Hoteling's t-square first to be 6.7, the observed value of the t-square statistic to be 6.7, because as we had seen for the second hypothesis for the given problem, it is that only, and H02 is rejected for this particular set of data of coincident profile of the test group and the control group, and hence we can say that the profiles are not coincident in this particular setup, and hence we do not have the coincident profile nature from this two, as it is quite evident from this that we have clearly two different profiles actually. This is profile for one group, this is profile for the other group, although they appear to be statistically parallel, but they are not coincident profiles, and hence the level profile hypothesis does not come into picture here, and we will have to be we'll have to stop at that particular point when we say that we have well parallel profile, but we do not have coincident profile, that is the profiles are not equal, they are different. So this is how profile analysis actually is carried out in practice. There are other applications also of Forteling's t-square statistic, like paired comparison, then repeated measure designs and all. So we are not going to go into detail of those. So they are similar problems which can be tackled under the similar type of approach what we have adopted for the profile analysis. Is basically Forteling's t-square is what is going to be used there as well. So from the next lecture what we are going to start is we are going to look at multivariate analysis of variance, comparison of more than two groups of means is what we are first going to see, and then we are going to look at the extension of univariate theory of analysis of variance to the multivariate data. Thank you.